If you had to guess which of these is more elastic, the stretching rubber band or the rigid steel bridge, the answer seems obvious. Human intuition points straight to the rubber band. But in the world of physics, solid steel is actually vastly more elastic than rubber. To understand why our instincts get this so backwards, we have to look at the true definition of elasticity, dig into a 17th century mathematical rule called Hooke's Law, and see how engineers use this paradox to ensure massive structures remain stable. The confusion starts with how we use the word elastic in everyday life. We think it means how far something can stretch. In physics, elasticity is the measure of how perfectly an object resists deformation and snaps back to its original state, using internal restoring forces. If you stretch a rubber band enough times, it eventually stays slightly loose. It permanently deforms. Steel, even under immense loads, returns to its original dimensions. To see how these materials truly compare, we need to move past observation and look at the math. Observe deformation with a metallic wire holding a weight pan. Adding weight creates a downward deforming force. The atoms instantly generate an upward restoring force. This restoring force per unit area is stress. The resulting change in length divided by original length is strain. These two variables are locked together. Increasing external weight forces atoms to generate higher internal stress, which physically manifests as a higher strain, or extension, on the wire. Calculating the precise ratio between the stress applied and the strain produced gives us the only objective way to score a material's elasticity without relying on guesswork. In 1660, an English physicist named Robert Hooke observed that this relationship was highly predictable. He noticed that as you increase the external weight, the physical extension of the material increases at a consistent rate. Graphing this principle puts strain on the horizontal axis and stress on the vertical, creating a straight diagonal line. This direct proportion is Hooke's law. Dividing stress by strain gives a constant value, the slope of this line, called the modulus of elasticity. This modulus provides the standardized score for elasticity. It ignores physical size, depending on fundamental properties. Looking back at our graph, we score our opening objects. Steel is incredibly steep, representing a high modulus. Rubber sits lower, with a shallow slope. That steep line shows the reality. Steel requires massive amounts of stress to produce even a tiny strain. Because it generates such powerful restoring forces, it yields a high modulus score, proving mathematically that steel is the more elastic material. But materials have their limits. If you keep piling on external weight, eventually the downward deforming force simply overwhelms those internal atomic restoring forces. Here is what that breaking point looks like on a graph. The straight line suddenly curves and drops. That inflection point is the elastic limit, the maximum threshold of stress a material can handle before it loses its ability to snap back. Push a material past that limit, and it enters what physicists call plastic deformation. The atomic bonds slip, and the material suffers a permanent shape change, eventually leading to a complete structural failure. Civil engineers rely on these modulus and elastic limit calculations every day. By knowing exactly where the math breaks down, they ensure that structures like skyscrapers and bridges never enter plastic deformation. There is, however, a hidden variable that can alter a material's modulus of elasticity from the inside out: temperature. As a material heats up, its atoms vibrate more violently. This thermal energy stretches and weakens the intermolecular bonds holding the atoms together. Weaker bonds mean weaker restoring forces. Without that strong internal pushback, the overall modulus of elasticity drops, making it more vulnerable to failure. Which brings us to a theoretical problem. If heating an object weakens its elasticity by loosening its atoms, what happens to a material's elastic properties if you freeze it down to absolute zero? Drop your hypotheses in the comment section below, and we'll test the best answers in our upcoming video on thermodynamics.